One of the biggest fundamentals in ghost hunting and paranormal research has to do with the phenomenon known as electromagnetism. A lot of ghost hunters think that ghosts are electromagnetically based, or perhaps some sort of electromagnetic interaction is occurring. So why did they actually think this? Well, here's a little chart to kind of help you out. Now, as you can see from the chart, everything points to electromagnetism. So it would only make sense that we know exactly what electromagnetism is and how it applies to ghosts. But to do that, yeah, we have to go over that boring science stuff. So here it is.
Electromagnetism is the physics of the electromagnetic field, a field encompassing all of space which exerts a force on particles that possess the property of electric charge, and in turn are affected by the presence and motion of those particles. The magnetic field is produced by the motion of electric charges, in other words, electrical current. The magnetic field causes the magnetic force associated with magnets. The term electromagnetism comes from the fact that electrical and magnetic forces are involved simultaneously. A changing magnetic field produces an electrical field, while a changing electrical field generates a magnetic field. Because of this interdependence of the electric and magnetic fields, it makes sense to consider them as a single coherent entity, the electromagnetic field. This unification, which was completed by James Clerk Maxwell, is one of the triumphs of 19th century physics. It had far-reaching consequences, one of which was the understanding of the nature of light. As it turns out, what is thought of as light is actually a propagating oscillatory disturbance in the electromagnetic field, in other words, an electromagnetic wave. Different frequencies of oscillation give rise to the different forms of electromagnetic radiation, from radio waves at their lowest frequencies, to visible light at their intermediate frequencies, to gamma rays at the highest frequencies. The theoretical implications of electromagnetism led to the development of special relativity by Albert Einstein in 1905.
So as you can see from the film, electromagnetism is pretty much the game. It's pretty much the energy that we're looking for. Anything paranormal is going to have energy of some sort. The movement of air requires energy, and that's why we're looking predominantly at the electromagnetic spectrum. Now here's a cute little film by NASA. I want to show it to you, and it kind of explains in general concepts what we're talking about.
Microwaves, visible light, and radio waves are all fundamentally the same thing. Electromagnetic radiation carried by particles called photons that radiate in waves. All photons travel at the same speed, the speed of light, but they vibrate at different rates depending on the amount of energy they're carrying. The many types of radiation are called the electromagnetic spectrum. Gamma rays, like the ones from a nuclear explosion, are high energy, and they vibrate at very high frequencies, 10 billion trillion times a second, or 10 billion trillion hertz. As you move down the spectrum, the energy decreases. X-rays vibrate at a lower frequency, followed by the ultraviolet rays that can give you a sunburn, and then the part of the electromagnetic spectrum our eyes can actually see, visible light.
Within the optical frequencies, the photons have enough energy to excite electrons in molecules, and that's the basis of how flowers grow and of how we see. Once we get down a little bit lower, down to lower frequencies now, into infrared, and then into the microwaves and radio frequencies, the photon energy isn't even enough to do that. But it can heat. And that's how a microwave oven works. It works by heating molecules. As the frequency gets a little lower, we now pass through the frequencies used for cellular phones. Then television and FM radio, and then even lower the ones used in broadcast AM radio.
Every day we're bathed in electromagnetic energy from all parts of the spectrum. Which parts of the electromagnetic spectrum were you exposed to in the past year? How about today?
So what kind of fields are we exposed to on a daily basis? Well, none of that matters. We could use Occam's razor to figure it out, but it's pointless for the training. The thing you need to know, though, is that brain waves are also electromagnetic phenomenon. So is the consciousness, at least according to Dr. John Joe McFadden. But one of the things that's important to point out about electromagnetism is this huge, massive theory that gets very detailed very quickly. In fact, there's only so much you can explain with words. You have to actually go into mathematics, calculus, vectors to explain the whole concept. But here's a simplified version aimed at giving you just enough knowledge to understand what you're looking at.
In general, electromagnetic sources produce both radiant energy, in other words, radiation, and non-radiant energy, which is fields. Radiated energy exists apart from its source and travels away from the source and continues to exist even if the source is turned off. Fields are not projected away into space and cease to exist when the energy source is turned off. For static electromagnetic fields, there is no radioactive component. Big element here of generalization is static electromagnetic sources do not produce radiation. So what units are used to measure electromagnetic fields? Well, first of all, we have to look at two primary components which are crucial to describing the properties of an electromagnetic field or an electromagnetic wave. The first is frequency. Frequency describes the number of waves that pass a fixed place in a given amount of time. So if the time it takes for a wave to pass is a half a second, the frequency is 2 per second. If it takes 1/100th of an hour, the frequency is 100 per hour. Usually, frequency is measured in the Hertz unit. This measurement is abbreviated Hz and is the number of waves that pass by per second. For example, an A note on a violin string vibrates at about 440 Hz, or 440 vibrations per second. The second element is wavelength. Forms of electromagnetic radiation like radio waves, light waves, or infrared heat waves make characteristic patterns as they travel through space. Each wave has a certain shape and length. The distance between the peaks, or the high points, is called the wavelength. Now, frequency and wavelength are related. As the frequency rises, the wavelength gets shorter. Power frequency fields are 50 or 60 Hz have a wavelength of about 5,000 kilometers. Static fields or direct current DC fields do not vary regularly with time and can be said to have a frequency of 0 Hz and an infinitely long wavelength. Now, the way the power or the intensity of the fields is measured is through various measurements. Static magnetic fields are generally measured in Tesla, which is abbreviated T, and variants of this, for example, millitesla and microtesla. And here's a conversion for those specific measurements. In the US, fields are sometimes still measured in Gauss and milligauss. As you can see, there's a little bit of a measurement here, but there's a huge difference between these two measures. 1 nanotesla equals 0.01 milligauss. Now, the reason this is important to understand, a lot of the instrumentation that we use measures in both, uses both measures. To give you an example, the natural tri-field meter measures in nanotesla, where a lot of our AC electromagnetic field meters measure in milligauss, and there's a huge difference between those two. So it's important to keep that in mind. Magnetic fields can be measured either as magnetic flux density or as magnetic field strength. In the US and in Western Europe, field strengths are usually specified in the units of magnetic flux density, either Tesla or Gauss. Now, it's also important to note that there are two different types of electromagnetic fields or electromagnetic waves, and they are basically AC or DC. AC, of course, stands for alternating current, while DC stands for direct current. Now, alternating current is a type of electricity commonly used in homes and businesses throughout the world. While the flow of electrons through a wire in a direct current, or DC, electricity is continuous in one direction, the current in AC electricity alternates in direction. The back and forth motion occurs between 50 and 60 times per second, depending on the electrical system of the country. AC is created by an AC electric generator, which determines the frequency. What is special about AC electricity is that the voltage can be readily changed, thus making it more suitable for long-distance transmission than DC electricity is.